It's a great pleasure to start the last session of this workshop with Nava Gaddam on the information paradox as a scattering problem. Thank you.
Great, thank you very much. It's an honor and I'm very happy to be speaking to you all. So thank you to the organizers for inviting me. And thanks to also my collaborator who was originally invited, who couldn't make it, so I get the chance to steal her time. I'm going to talk about the information paradox as a scattering problem. It's perhaps something that's an old-fashioned perspective, but I hope I can shed some new light on it, especially to this audience. I've particularly enjoyed the workshop and there were many talks that were very interesting and inspiring. Unfortunately, I couldn't follow a lot of them in real time, but I'm glad that they're recorded. There were also some comments that I would have probably liked to make in some of the discussion sessions, but now is my chance. I hope that you will interrupt me whenever there are questions. I don't really have to get to the end of my talk. I'd be much happier if people could stay with me till wherever I got. And if I'm running out of time, the burden's on me to find my way to converge to some sort of a meaningful end. So let me begin. Do you see my slides moving?
Yes, it's fine, yeah.
Okay, great. So this talk is mostly based on a couple of papers that I wrote towards the end of last year. One is with Nico Groenenboom, who's a student who just began a PhD with us. And another is with Nico and Gerard Hoofs, with whom I work in Utrecht here. And I will also refer to some work in progress and make some passing comments about some older work with Panos Betsios and Olga Papadoulaki. And the references are here. So here's where I'd like to begin. Essentially, this entire workshop and conference is very much about gravitational interactions. And it begs the question of how we can think about information loss, the paradox that Hawking posed when you include interactions. He showed that when you have free field theory on curved spacetimes, then there's a sense in which information is lost when you map modes that are received at Scri plus to modes that are injected from Scri minus. So a very quick whirlwind perspective of what I'm going to show, or what I would like to discuss, is this. When you have small enough impact parameters, and of course all of you know this, and I'll be precise about all the scales in the game, but when you have small enough impact parameters and high energy scattering, it's expected that there's large black hole formation, classically already. And therefore we expect that there's strong gravitational effects, so you cannot ignore gravitational interactions. And you can ask, what are the set of all out states? Where does the entropy come from a scattering perspective? And is there even a regime in phase space in effective field theory where amplitudes are at all calculable? And you might wonder, why should such a regime exist? I don't have any strong claims or proof that it should, but very naively, you might think that from various perspectives, also string theory and holography, ADS-CFT, there are many indications that the information problem can possibly be resolved within an effective field theory that is effective to some reasonable extent. And there's also, of course, it's well established that gravity is sort of special in the sense that quantum effects arise from not just momentum transfer like in quantum field theory, but also from emergent scales, where information loss or the entropy of a black hole is a classic example, of course. And there's a sense in which things classicalize. So presumably one might expect that such a regime could exist. And in this talk, I would like to propose a regime in effective field theory, which I think captures this the problem of black hole evolution, and where you can also calculate some amplitudes. And there's a similar sense of eikonalization or exponentiation of the leading eikonal. And in this regime, one can ask several interesting questions. So for example, once I'm able to compute some amplitudes, is there a sense in which entropy emerges, or can I see entropy coming in somewhere? And if I'm working with black holes, is there a sense in which one can go from the standard post-Newtonian expansion to the post-black hole expansion, which I would like to advertise? Where do all the time scales in black holes arise from? For example, scrambling time or page time. And what happens to IR divergences when you have an infrared emergent scale like the Schwarzschild radius? There's also some talk about antipodal identification and BMS that was mentioned earlier in the week that I would also like to allude to. So here's a plan for my talk. I'll first quickly review large impact parameters and the familiar flat space eikonal. It's very familiar to you all, so I hope to go rather quickly there. But then I will try to introduce what I would like to distinguish from the flat space eikonal. I call it the black hole eikonal phase. And this is where I would like to compute some amplitudes, and in particular, show you the 2 to 2 amplitude. And then after that, I will have the floor open to sort of be able to make several comments. Some of the comments I will already make when I introduce the black hole eikonal phase. So here's where I begin with large impact parameters. So of course, we know that I'm going to work in the Minkowski diamond instead of the half diamond. So naively speaking, you might want to think of every point on this diamond as a half sphere. So points on the right are antipodally related to points on the left, if you will. And if you think of particles that are scattering at large enough impact parameters, where large is what I write here, that it's greater than the scale associated to the scattering energy, so g Newton times square root of s, which is also much larger than the Planck scale, then we know that there's a classical shift that can be seen in nonlinear Einstein's equations called the Eichelberg-Sechsel shock wave. There are many people who worked on this. You cannot ignore back reaction in this case, of course. And these are known to be generated, for example, by the 3-point vertex with the graviton above the Minkowskian background couples to the stress tensor of the particles moving in. The leading eikonal, of course, has a familiar form, and that's determined in terms of the center of mass energies, Mandelstam variables S and T, and is determined by an infrared mass regulator and the impact parameter B. And the form of this is, of course, important, that it's log of B. And I will show how this is in contrast to what I will now define to be the black hole eikonal phase soon. Yeah, of course, many people have spoken about this also in this workshop, Carlo Heisenberg, Stock, Ludovic Plante, Mao Chang. There are many other people who've made references to it. These can be, yeah, there's a lot that has been done. Excuse me if I'm missing some references. I'm still diving into this literature myself. So where are the black holes in this story? There are no black holes so far, but they appear as an intermediate state, or expected to appear as an intermediate state, when impact parameters reach are no longer much greater than g Newton times square root of s, but as they reach this emergence scale. And this is again an illustration in some sense of the fact that gravity is sort of special because there are emergence scales in the game. And now another interesting scale, which is in the ultraviolet that one can think of, is a string length, of course. So when you think of stringy corrections, if I'm at weak string coupling, there are essentially 3 length scales that one can think of: the impact parameter of the collisions, the Schwarzschild radius, and the string length. And the flat space eikonal so far is, of course, when the impact parameter is much greater than the Schwarzschild radius and also much greater than the string length. And of course, this can be corrected. There are classical corrections that come because of, for example, the H diagram, or quantum corrections that come because of vertex corrections and additional and so on. This is also interesting because another regime that one could worry about is when the string scale is much greater than both the Schwarzschild radius and the impact parameter. And in this case, of course, the stringy effects start to dominate before classical black hole production occurs. And it was noticed by several authors that I list above, that as the string length is scaled towards the Schwarzschild radius, there's a sense in which black hole-like behavior emerges. And this also goes under the name of black hole string transition, where on the expression at the bottom left, you see that as one tunes G string to be small or large, one can go to the regime where the string length is greater than the Schwarzschild radius or vice versa. And of course, there's a third regime where impact parameters are smaller than the Schwarzschild radius. And this is where we expect classical black hole production to appear. And this is what I want to focus on today. And as I just said, by tuning G string, one might look at the black hole string transition. So what do I have in mind? A very naive picture where I think of high energy scattering, where the center of mass energy is roughly the square of the black hole mass that is to be formed. And I'm thinking of impact parameters that are smaller than g Newton times square root of s. But I also want to stay away from things that I have absolutely no control over. For example, Planckian effects. I want to keep my impact parameters to be larger than the Planck scale. And this is the regime that I'm roughly interested in. That's where I would go to next, with smaller impact parameters. But maybe it's a good time to pause if there are any questions with what I'm going to say or with what I've just said so far. I'll give it a few seconds. Okay, if there are no questions so far, let me move on. So how do we think of smaller impact parameters? Of course, gravitational effects are expected to be very strong. So it's not really clear how one should go about it. And here's a picture that I want to use as inspiration. And it's the following. It is that when we think of collapse due to infalling matter, of course, long after collapse, we think of the event horizon, but already during the collapse, the event horizon is very different from what is called the apparent horizon, which forms during collapse. And as the collapse settles down, the apparent horizon very naively begins to agree with what we think of as the event horizon. But in the initial stages of the collapse, of course, they're very different. Now, the time of collapse for a large black hole is very small compared to the entire lifetime of the black hole. So one can think of, for most of the lifetime of the black hole, as particles are falling in or radially moving inwards, they can be thought of as falling into an already existing black hole horizon. Of course, this approximation gets better if I think of these particles as falling in long after the black hole is formed. So as some probe particles that I throw in. But in some sense, towards the end of the collapse, this approximation already is reasonable. And so essentially what one misses in this game, or when you make this approximation, is all the effects associated to the initial stages of the collapse, perhaps all the effects that are in the final stages of the collapse. So what I want to now do is, instead of working with excitations or propagators of the graviton around the background, which is the Minkowskian metric, I want to think of perturbations and all the interactions that are governed by the propagator that arises from an existing Schwarzschild background. And this is where I want to think of as a phase that is different to the flat space eikonal, and I want to call this the black hole eikonal. In some sense, this is it's not radically new, but it has very interesting physics that that I think, to my knowledge, hasn't been noticed yet. So as I said, I'm going to think of this phase as matter fields that are propagating on an existing black hole background. And these are, for example, generated by similar 3-point interactions and higher order interactions, of course. But now in this, when you have a Schwarzschild background, it's no longer true that the de Dohmler gauge is not necessarily the most convenient gauge. It couples, for example, all the different spherical harmonics. But the famous Regge-Wheeler gauge is a convenient enough gauge where all the spherical harmonics decouple at the quadratic order at least. And the gauge very schematically is what I write here, where you split the metric perturbations around the black hole background into even and odd parity gravitons. So the even parity graviton is the block diagonal piece that you see. It has a 2x2 metric perturbation, which I label as HAB. So this is a symmetric 2x2 matrix. It has 3 components. K is a scalar on the transverse directions, and X carries 2 degrees of freedom, and that's the odd parity graviton. So together they make up the 6 physical off-shell degrees of freedom. And in this gauge, one can show that all the spherical harmonics decouple. It's very well known. We also wrote it down in a paper with Nico. And what's also interesting is that as long as one ignores or thinks of transverse momenta along the transverse directions to be small, then the odd parity graviton also decouples from the even parity graviton mode. And now I want to think of scattering processes which are approximately spherically symmetric. This is not necessary. One can just work with Klebsch-Gordon coefficients that arise from a 3-point interaction. But if you think of a large black hole with interactions of small particles on top of this background, this process, strictly speaking, breaks spherical symmetry, but you don't imagine that it completely destroys the spherical symmetry of the entire solution. So at every 3 vertex, I draw a solid line and a dashed line, where by a solid line, I denote the one that carries L and M indices, so the angular momentum indices. And the dashed line I think of as a spherically symmetric mode, or with some fixed angular momentum. So a tree level diagram would look like so on the right-hand side of your screens. And you see that the angular momentum Lm goes from P1 to P4 at tree level. But as you build your ladder diagrams, the angular momentum doesn't necessarily go down, but can also stay on top, as I will draw in a couple of slides. So here,
may I ask a question?
Yes, please.
I didn't quite understand this latter explanation of this figure. P1 and P2 represent, can you repeat?
So P1 and P2 represent particles that are traveling along the light cone directions.
Okay.
And P3 and P4 are the outgoing modes.
Okay. On the Schwarzschild metric.
Correct. So what I want to think of is particles that are drawn here. So P1 and P2 would be the red and green ones. And I want to think of particles emerging in the top.
Yeah. Yeah. Is the gravitational S matrix in the sense of Toft?
Exactly. Exactly. And I will show that this way of thinking about it is probably familiar to all the amplitude calculations, but it recovers very nicely the S matrix of a Toft with some important differences. But I will point these out a little later.
Thank you.
Any other questions? Okay, so here's sort of an overview of what I want to call as the black hole eikonal phase. I'm thinking of particles that are scattering near the black hole horizon. So they are confined to a sphere that is of roughly the order of the Schwarzschild horizon. So impact parameters are naturally of this order of the Schwarzschild horizon or can be much smaller. But as I said, I want to stay away from Planckian effects. And I've also assumed that transverse momentum effects can be ignored and spherical symmetry is approximately preserved. Now what happens is that because I'm working, I integrate out the sphere, I'm working in a partial wave basis, an emergent coupling constant arises which governs the interaction vertices, which is what I call gamma here, which is roughly m Planck over m black hole. And if you think of massless particles in the flat space eikonal, they have ultra high energy scattering. So the energy of scattering is much greater than is trans-Planckian, if you will. But in this case, because of the emergent scale, that condition is much more relaxed. There's a suppression factor which comes because of gamma. So for large black holes, the window of applicability of this calculation is very wide. And the Feynman rules can be derived. And this is a propagator that we wrote down near the horizon. To my knowledge, the analytical propagator on a Schwarzschild background is not known, but near the horizon, one can write this down. And that's what we wrote down in our paper. So the Feynman rules, as you see, for the scalar legs, I started with massless scalars, but there's a very small mass effectively in 2 dimensions that is picked up, which is inversely proportional to the Schwarzschild radius squared. And the graviton propagator has very interesting properties now. So firstly, the near horizon region is essentially conformally flat, where the conformal factor carries a Watt factor that you see in the metric. So there's the emergent scale of the Schwarzschild radius sits inside the conformal flat piece. So if you look at the momentum independent pieces in the metric, in the propagator, on the far right of your scheme, you see something that looks like flat space, but now I have only 2-dimensional indices, A, B, C, D. And there's a conformal factor which has the emergent scale, the Schwarzschild radius. And there are, of course, momentum dependent pieces. So there are familiar UV divergences, so nothing is, I haven't solved any problems here. They remain as you send K to infinity. But very interestingly, this is naturally infrared regulated. The graviton, if you will, picks up an effective 2D mass because of the curvature. So the 4-dimensional graviton is still massless. Nothing has happened there. It's just because I've reduced the problem to 2D, it picks up the mass in terms of a potential. And so in all my Feynman diagram calculations, there are no infrared divergences, which is very interesting. And it's in contrast to what you see in the flat space eikonal, where you have to explicitly insert a regulator. And as I said, the vertex is specified by a coupling constant, which is gamma, m Planck over m black hole. Perhaps a couple of interesting things that I don't understand very well myself yet, but are probably important, is you see lambda, which is L squared plus L plus 1, appears with the lambda minus 3 in the denominator in the momentum dependent part of the propagator. So in particular, when L equals 1, it's like the center of mass motion of the black hole. There's presumably some additional gauge redundancy that needs to be thought about. And if I'm looking at the spherically symmetric part compared to the large L modes, there's a sign flip in front of the momentum piece of the metric, of the propagator, sorry. I don't completely understand the L equals 0 and L equals 1 mode. But these will be unimportant, at least in the 2 to 2 eikonal. because everything gets projected into the soft sector, you get the familiar delta functions in the momentum. So that piece becomes irrelevant for now. So in the 2 to 2 amplitudes in this black hole eikonal, we have 3 scales in the problem. So it's Planck mass, the black hole mass, and the energy of the collision. So I'm going to sum over all ladder diagrams, just like in the flat space eikonal. So that's all orders of gamma. Well, you might want to call it perturbatively exact instead of non-perturbative. But I'm going to stay perturbatively in the large energy limit compared to gamma times m Planck. So this just means that if the consequence of working perturbatively in this limit is that only soft diagrams contribute. It's just an outcome. So here's a box diagram, for example. And here you see that at one loop in the box diagram, because every vertex contains one solid line and one dashed line, so one line with angular momentum, the other one without, the solid line stays on top. So I want to call it the conserved channel. It's just a name that is unnecessary, but where the angular momentum stays on top of the diagram. Whereas if you think of 2 loop diagrams, a double box, then you see that the solid line goes to the bottom, where it gets transferred across the gravitons. Just like in the flat space eikonal, you can write down all the n loop amplitudes, all the ladder diagrams. And again, everything is determined in terms of one eikonal function, which is again projected to the soft limit. But now, because I've already integrated out the sphere, you don't see the q perpendicular integrals. You only see the 2-dimensional theory and with every partial wave. The other interesting thing, which is now strongly in contrast to the flat space eikonal, is that it's dominated by low L modes. If I remember correctly, the flat space eikonal is dominated by the large L modes, whereas now it's dominated by the low L modes in the black hole eikonal. Is this a good? Yeah, perhaps I will make a comment in a couple of seconds. But before that, again, just like in the flat space eikonal, you can just resum all of these and you get a nice exponential, which is again very similar to the flat space eikonal. But now there's an interesting factor of 2, which is different. So if you think of L equals 0, the Drey 't Hooft shock wave, which is the shock wave S matrix that 't Hooft has been working with so far, it has an L squared plus L plus 1 in the denominator in this exponential. Whereas if you do the eikonal calculation, you get an L squared plus L plus 2. So in particular, for the L equals 0 mode, this is a factor of 2. Earlier in the week, and on many occasions before, Gabriele has made some comments about a similar factor of 2 discrepancy when one thinks of the flat space eikonal, which is fixed when you include the Gibbons-Hawking term to the action. Presumably something similar may happen here. I don't really know exactly how that works, but one can show that in the eikonal, if you restrict your graviton perturbations to also be on shell, then you will get an L squared plus L plus 1. But if you include also off-shell fluctuations in your virtual gravitons, then you just get what you get, L squared plus L plus 2. This is an interesting factor of 2 that probably deserves some attention. I see. So let me move on now to making some additional comments. So I've already made some comments about on-shell versus off-shell. There's an interesting factor of 2. And some comments about IR divergences. There are a few other things that I could say, but before I go there, let me pause to ask if there are any questions.
I have a question.
Yes, please.
Why in your diagrams, one of the particle is spherically symmetric? So you draw this 2 to 2 diagram where you have one particle, a solid line, and then a dashed line, yes. Why in the final state there should be a spherically symmetric particle?
There needn't be. In principle, you could just write down all the Clebsch-Gordon coefficients and the exponentiation works. It's just that I chose to do the simple thing to write down simpler looking expressions. This needn't be the case. And in fact, spherical symmetry is just broken by the interactions. What I wanted to say was that if there's a large black hole and I'm thinking of particles that interact and the collision is of a shorter time scale. It doesn't necessarily destroy the spherical symmetry of the large black hole. So in some sense, there's an approximate spherical symmetry. So I was saying that I could do this, but this is not necessary. And in practice, strictly speaking, this is not true. And one would have to write down the Clebsch-Gordon coefficient.
Okay, thanks.
Any other questions?
Yeah, so can you go, did you write down the S matrix expression, the analog of the gamma over gamma times range type thing?
Excellent. So here I'm working in global Kruskal coordinates because I drew the global Minkowski diamond, right? And I'm thinking of U and V coordinates there. And you could work with exponentiated coordinates near the horizon, because the effect that I'm talking about is near the horizon. And then you would have to, and then you get, you get an S matrix which has gamma functions, which looks exactly like a Thorpe's, except that in the partial wave basis, you have a different factor with the L squared plus L plus 1. I just haven't written the expression here. Okay, and I don't know if it's good time to ask this question, but shouldn't you expect some kind of exponential suppression of 2 to 2 in gravity? Yeah, perhaps a good question. You should. Is it visible in this expression here? No. So the way I would like to think, yeah, perhaps if you hang on for a couple of minutes, yeah, maybe it's a better point for me to make this comment. Okay. Thanks.
Nava, I know we had a lot of questions. Maybe if you can wrap up in the next 5 to 10 minutes so we can take questions at the end.
Yes, that's great. I'm almost there. So some comments. So in principle, nobody told me that the out states are only 2 particles. So one could ask, can I write down amplitudes which are 2 to n? And one can. In particular, again, in the same limit where I have the center of mass energy is mass of the black hole squared in the same limit. So I'm still in the same eikonal limit, but you could write down 2 to n amplitudes, what we're working on now. So here's a couple of tree level diagrams. So the one on the left and one is something that you might want to call as a T channel. The one on the right is an S channel diagram, where in the out states, momentum conservation tells you that all the particles will start to be soft, in the sense that as the number of particles increase, the momentum is distributed among all of those. However, now you see, in contrast to the 2 to 2 amplitude, momentum transfer becomes important. So the virtual gravitons are no longer soft. There are many out states allowed. In principle, I could ask this question about all n. Very interestingly, all these diagrams are calculable, of course, at tree level, but we have evidence so far that even the exponentiation carries through. In the flat space eikonal, that's very difficult to see because you have the transverse momentum integral. Whereas in the flat, because right now I'm in 2 dimensions on the black hole on a partial wave basis, I haven't written down expressions here because we're not yet sure of the final expression, but it looks like you can replace every 2 to 2 part of this diagram with an entire eikonal. So you replace the graviton propagator by the entire eikonal piece. And it looks like a natural exponentiation for 2 to n amplitudes can come out, which is very interesting. It may lead to what is, so people have worked with 2 to 2 amplitudes and argued that this leads to some sort of a chaos bound. I don't have time to get in there, but if one is able to exponentiate, one of the consequences would be an endpoint chaos bound, for example. What's also interesting is related to a question that was just asked. If you have 2 to 2 scattering, if you write it down in the appropriate coordinates where you have the gamma functions visible instead of the global Kruskal coordinates that I wrote down, one can compute the time delay associated to the scattering process. The same thing has been done in flat space. And what you actually get in this case, if you do this, is a scrambling time. So in the 2 to 2 process, the time delay associated with the scattering matrix is m log m, if you wish. That's the scrambling time associated to the black hole. But now you could ask, is there a Wigner's time delay associated to 2 to n scattering amplitudes? Is that longer? And one may wonder if a sum over all of these gives you a longer time scale than scrambling time. And in some sense, the exponential suppression probably comes from the fact that one has to sum over all possible out states, each of which is perhaps suppressed. So if you compute 2 to n amplitudes, I expect that you will explicitly see an e to the or n to the n suppression or e to the n suppression in these amplitudes. But this is still work in progress. I don't have explicit expressions, unfortunately, to show you yet. Some other comments, antipodal identification. So there's some confusion, I think, which comes from thinking of antipodal matching that originates at spatial infinity when one studies BMS symmetries. So this antipodal identification comes because one has to match modes on scry minus with modes on scry plus at spatial infinity. Whereas what the antipodal identification that 't Hooft has been proposing comes because we're just working on a Minkowski diamond or on the two-sided black hole metric, if you will, which to my mind is a condition on the horizon and not at spatial infinity. I don't understand everything about it, but there are characteristic differences and the antipodal identifications are not the same. With BMS, there are no IR divergences in this problem, as I said, because of the emergent scale. So if one was one was a relativist and asking about conservation laws and one expects conservation laws to be violated, if there are infra divergences, you would rephrase that to say that there's no violation of conservation laws in this case because there are no IR divergences. And it's also, one can also show Hawking, Perry, and Strominger have made some progress to this end. And there's some work in progress that I'm doing where one can show that shock waves imprint supercharges on the horizon, super translation, and actually also super rotation charges. So there's some interesting physics that's associated to symmetries near the horizon that's in some sense analogous to BMS that can be worked out, but the entire picture is not clear. Perhaps a final comment that I'd like to make is that, of course, I worked with 3-point vertices and I showed you a 2 to 2 amplitude. And there's a natural G Newton expansion from the black hole eikonal, just like in the flat space eikonal. So you might wonder, if you think of the two-body problem, when impact parameters get smaller, if in the post-Minkowskian approximation, instead of looking at Minkowskian propagators, one might want to consider using the black hole graviton propagator and ask about an effective one-body formulation of this problem. And as I said, unlike in the flat space eikonal, the black hole eikonal is dominated by low energy angular momentum modes. So if you have two spinning particles, which somehow can be exchanging graviton propagators, which is dominated by low L modes, but the spinning particles have angular momentum, there's probably some interesting physics that emerges out of this. I haven't thought about it carefully, but I just see that it's a possibility. And it's perhaps in line with a lot of work that's been displayed in this workshop. So to conclude, what should you ideally take away from this talk? One is that there seems to be a remarkable new phase in quantum gravity, which captures, to my mind, black hole evolution with some, in some controlled regime where amplitudes can be calculated. And there's no UV completion necessary here. And I think with 2 to n amplitudes, the exponential suppression emerges naturally. It was also seen in 2 to n amplitudes in the flat space case. And I think this is a very natural place where information paradox can be addressed. And you can ask what happens if I include stringy corrections and treat the black hole string transition. There's also a very interesting story with gravitational echoes that emerge from the scattering near the horizon. When you match that with the transfer matrix associated with the classical potential further away from the horizon. That's some work that I've written down with Panos Betsios and Olga Papadoulaki towards the end of last year, but unfortunately I haven't had the time to discuss it. And there's of course a whole lot of additional work that one can do. And I'll just leave that slide with some further ideas and thoughts and take more questions. And thank you for your time and attention.
Thank you very much. That was a fascinating talk. Thank you.
Thank you.
So we have a lot of time for questions. I know we had a few already, but maybe we can follow up on some of the discussions.
If I may, thanks for the comments on the exponential suppression, but I'm not sure I followed them really, because, or at least the connection with 2 to n, because the reason why 2 to 2 is suppressed is because the black hole wants to decay to n rather than to 2. And I'm not sure I got the connection. And did you make a statement that when you write your amplitude in those different coordinates as a function of s and t, you have an exponential suppression for the 2 to 2 S matrix, or or not?
Okay, I'll answer the second question first. No,
Okay.
that's not what I want to say. Exponential suppression in that sense is not visible because of a coordinate change. I just wanted to say that the gamma matrix representation of the scattering matrix is visible in different coordinates. What I want to say with the exponential suppression, I was probably a bit too quick there. When you compute a 2 to n amplitude, you can write down a general expression for what the 2 to n amplitude looks like. And then if you look for a saddle point, this amplitude has a nice behavior which is relatively sharply peaked for a specific n. And it's still work in progress, so I'm not sure how much of what I'm saying is speculation and because of mistakes that we're making, or how much is really true. But one interesting feature seems to be that there's a scaling that comes about because of n. And if one of the n's is dominant, then all the others are suppressed. In particular, 2 to 2 are suppressed relative to the dominant contribution. So I think an exponential suppression can emerge, and probably does emerge. I don't have a completely clear story in my head. I just see it happening in some of the calculations that we're doing now.
Okay, thank you.
May I try to understand better? So this is 2 to n in the presence of the black hole, right?
Yes.
So at small impact parameter? I mean,
yes.
what is the relative impact parameter of
the impact
particle
parameter
and the black hole? I mean,
the particles are interacting on the horizon or very near to the horizon.
Okay.
And the distance, the impact parameter between the interacting particles is therefore smaller than the Schwarzschild radius.
So they fall into the black hole in principle, classic.
In principle, yes.
So what should come out is Hawking radiation, or what? Stimulated Hawking? I don't see really the process.
Yeah, so what I'm imagining is that two particles fall into the black hole, right, and I'm computing the amplitude of n particles emerging from the other side.
From the other side.
Which would, in principle, and I'm trying to see if there's any way in which one can write down the emerging particles as Hawking radiation, and therefore with some entropic scaling with additional features of an oscillation that arises from the exponential.
Mm-hmm.
But whether this picture holds, whether this, how this exactly works is still work in progress. But I just wanted to show that the 2 to 2 amplitude neatly works. Mm-hmm. And in some sense, you might want to think of this as a scattering matrix for the black hole. Very detailed questions about what happens near the potential or near the black hole is a bit harder because I'm computing Feynman diagrams. So I have a map between asymptotic states.
Okay.
So it's a bit harder to understand exactly what the states are in relation to the black hole in the intermediate state. And
your E in the formula is the energy of the two particles, or
yes,
the total energy of the system? What is it?
Right. So in principle, when I do this calculation, I could I would have the E that appears, for example, here, the capital E that appears here.
What is that E? Yeah.
This E is the center of mass energy of the two particles.
Oh, okay. No black hole in that E.
No black hole in that E yet.
And you take this E to be much larger than M Planck.
Yes. No.
Or smaller.
I take this E
that
to
is
be
gamma.
Yes, I take this E to be much larger than gamma times M Planck.
You mean that define? And gamma is what?
Gamma is M Planck over M black hole.
Okay.
So this calculation is valid when E is much greater than gamma times M Planck.
So M Planck square over, okay, over the M of the black hole.
Right.
So E times M black hole much bigger than M square. Okay, then M Planck square. Okay, yeah, because I think it's true. The relevant quantity should be E times the mass of the black hole.
Indeed.
Yeah. And may I also ask a question about this antipodal identification in your case and relative to, say, what Strominger, for instance, was telling us about?
Mm-hmm. So here, as you see, because I've opened up the Minkowski half diamond, the particles that are reaching on Scri+.
He also did, by the way. He
Sorry?
also did. He also, Strominger did open it up.
Right, right. Well, yes, what I want to say is that the particles that are reaching Scri+, the two red particles that are reaching future null infinity, they are reaching antipodal points on the future null sphere.
Yeah, no, that's not what he meant by this.
Exactly. Whereas what Strominger has in mind is an antipodal matching that comes from the past of Scri+ with the future of Scri-.
Exactly, antipodal in this diagonal way.
Exactly. In principle, they have absolutely nothing to do with each other. That's my punchline comment, if you will. At least so far, in principle, it's not clear to me that they're related at all.
No, they don't look to be related.
Exactly.
But your antipodal simply means that the two particles come from two antipodal angles on the sphere.
Exactly. Which means that if you trace them back onto the horizon, they emerge, particles emerging from the North Pole and the South Pole of the black hole as outgoing radiation, that those will be antipodally correlated.
Okay, thank you.
So in some sense, this makes the horizon a projective sphere in Toph's language.
Mm-hmm.
Okay, we have time for one last quick question.
Can I ask a quick question?
Please.
So I was a bit confused, probably. Sorry. So at some point you drew the diagram for the collapsing matter producing the black hole, and you argued that you could approximate the late, let's say, apparent horizon with a eternal horizon. Did I get it right?
Yes. Yes.
But then when you drew the other diagrams later on, you didn't draw the standard Penrose diagram for an eternal black hole, right? The one with the singularity on the top.
Correct. Correct. What I want
yeah.
Indeed, because I'm calculating S matrix elements, these are asymptotic states. So I think of states that are ingoing long before anything has happened, and states that are received near Scri+, future infinity, long after everything has happened near the potential. So in principle, I'd like to think of particles. I would ask, when is it that I have ingoing matter that would collapse into a black hole? And my naive argument is that if there are particles that are interacting at impact parameters that compare to the scale of the energy of the collision, then I would think of this collision as producing a black hole. And then I'm computing amplitudes that map in states of this kind to out states, to any out states of n particles. This argument, what I wanted to give is that in principle, you could think of this process as being done on an already existing black hole, in which case there's just a black hole that exists for a long time, and I throw in two particles, and two additional particles or n additional particles come out, and I'm writing down a matrix between these two. These two states, in and out states. What I wanted to argue with this was that in principle, this picture also holds not only for particles that are thrown long after some black hole is formed, but as you go backwards in time, or if you think of particles that are falling in towards the final stages of the collapse, so these would be particles that would make up the black hole long after collapse, that this picture still holds, because essentially what I need is the propagator of the graviton near the horizon. And I'm calculating the propagator near the event horizon. And I'm just saying that if I look at the apparent horizon, it already begins to agree with the event horizon towards the final stages of the collapse. I don't have to wait long after the collapse. That's comment one. And if you think of the 2-to-2 amplitude, it's dominated by the zero momentum sector of the propagator. So even if I were to compute, let's say somebody gave me the propagator on a complete Schwarzschild black hole with a dynamical collapse, I would still, if you think that the 2-to-2 amplitude is still dominated by the zero momentum sector, the constant that I have in the zero momentum sector of the propagator would be some other constant. But the exponentiation and the entire story would not change. Some numerical values would change, at least when there's no momentum transfer.
I see. Thanks.
Okay, I think it's a good time to stop. So let's thank Nava again.
Thank you very much. Thank you.